All right. Good job. Good job on the homework. Pictures drawn, all that stuff. So hopefully that second day going through that was helpful in understanding. And so, and I was like, I told third block, um, you know, that's the key. And I told you this a little bit yesterday. It's like a do-over a little bit here, chapter 5, right? From the sense of these fundamental kind of concepts. And it's really the next several days, some of those concepts, especially these last couple of days, have been notation. You understand this integral notation and area notation, feel comfortable with finding these areas. So far, mostly it's just been about geometry, right? It's been about rectangles, trapezoids, and triangles, and circles, and stuff like that. And just getting us comfortable with that notation of area and so forth. So now we're going to move into more conceptual kind of stuff, kind of like when we did the chart, okay, derivative, slope, estimating slope. Remember we did a lot of that. We just kind of drew little slope triangles, and we did that way of estimating. And then we moved into the concepts, which led to the chart, right, with f prime being the slope function. We're going to talk about that a little bit today, how we got the idea of we can do more than just calculate one slope at a point. We can calculate the slope at all points, and that became the slope function, the y prime function, right? And then we talked about the y prime function, what that meant, and that its connection to the y function. When y prime is positive, y is increasing. When y prime is negative, y is decreasing. And we came up with all those connections, which led us into all the uses of the derivative, right? Well, that's going to be kind of what we're going to do now as well. We're at the point where we were able to do like one slope, like the slope triangle, estimated slope. Right now we can do a fixed piece of area. We can do the area from 0 to 2, the area from 1 to 4, the area from whatever, as long as it's got geometry in it, right? If it doesn't have geometry, we don't know how to do that yet. Well, the way we're going to learn how to do it over the course of the next couple of days is we're going to connect it to this idea of the derivative, how it's connected to that. And that's going to be the key to allowing us to do that. Okay? So there's a lot of conceptual kinds of ideas coming over the next couple of days. Today is one of my favorite days of the whole year. Very excited. Busy. We got basketball game and all this stuff. It's just crazy. All this stuff. Great day. I don't want to build it up too much because you might just be that bad. It might not be that great. You might not think it's as great as I do. Now, with that said, unfortunately with the snow days and everything, things have gotten a little bit messed up here with kind of the plan of what I want to do. Actually, we had this happen last year, but there was only 2 snow days last week. I don't know if you knew that. We had a couple snow days last year, the same week. And what I did, because originally in the plan, the quiz would be this Friday. Well, we don't even have school this Friday because it's parent teacher conferences because they're off week, whatever. Well, so we would have gotten to a quiz towards the end of this week. Well, we're not going to. Last year, I kind of pushed things up a little bit. We did do the quiz. So I thought that'd be better than doing it after a 3-day weekend, with parent teacher conferences last year. So we went ahead and did it. At the end, I think I regretted it. Maybe not as much as the students regretted it. They may have wanted it more, but they kind of wanted to get it done. So we're definitely not going to have a quiz this week. Ours is going to be next week, probably, maybe by Tuesday, possibly. Wednesday at the latest, but I'm thinking more like Tuesday. Okay. Now, with that said, I have to be gone tomorrow. And as much as I'm sure you would enjoy just having an hour to just sit here and look at each other and visit and talk, we're not going to do that because it does put us behind a little bit in getting done what we want to do. And what will get cut out, if we have to cut out stuff, is review time at the end of the year, like with the final exam and stuff. We don't want to cut out any more than that than we have to. So we do need, so we can't afford to just not do anything tomorrow. Luckily, I've got videos, right, from other years. Yeah, I know. So I apologize for that. So, but that's what you're gonna do in class tomorrow. You're gonna watch the video on your Chromebook. So bring headphones and your Chromebooks tomorrow. Okay. Now, if you want to do it outside of class and skip. Well, no, I would never advocate that. But whatever. But that's what you're going to do. Those are going to be my directions for the sub. You're going to have, so just like I was up lecturing, nice thing is you can pause, right? Yeah, pause me. Well, you could, I suppose, but it just takes stop with it. But it's a about 45, 50 minutes, and I think classes tomorrow about an hour and 10 or something like that. So I would treat it just like a regular lecture, right? I would have your notebook out, take notes. Now, the first part of it, I'm going to go over the homework that I assigned today, just like we normally would, and just like I did last year. It's from last year, okay? And so there'll be some weird things. I mean, there'll be some things that you'll hear. It'll talk about the quiz on Friday. Well, we're not having a quiz. We have school on Friday, so don't worry about that. Okay, so there may be some things in there that sound kind of strange, referring to something that was from last year, okay? But for the most part, it'll be going over the homework that I assigned tonight. It'll be going through that. It'll be talking about whatever new stuff. And so if I talked about writing it down in your notes, you might want to do that as you go along, okay? And then the assignment that I assign at the end of that, and I'll tell the sub this, is going to change a little bit. I'm actually going to, because we were pushing a little bit to get to the quiz, so I made the assignment a little longer than I'm going to make it for you. Okay? Especially since I'm making you sit through that video. Although, I don't know if that's any worse than sitting here listening to me. Just as boring. So, it'll be about the same. But so I may change the assignment at the end. Okay, a little bit. And so I'll tell the sub about that. So you make sure you know that. And some of the stuff at the end, like I think there's something in there in the video I say, well, because we're pushing up the quiz up, there might be something I'll cut out of the quiz or whatever. You know, I'm not going to do that this year because we're going to have time to make sure we get all that taken care of. Yes. Yes. Thank you. So anyway, that is the plan. That is, bring your Chromebooks, bring your headphones to do that. All right. So let's talk about today's on the packet just quickly here. This was just setting up. I mean, a few of you came in, had some good questions, mostly about stuff at the end. Most of this you probably found pretty easy. I hope, like number 4, for example, is just the integral from 0 to 2. You put the function right there. You put a dx there at the end. I suppose if you wanted to get really creative and or that type of person that just wanted to be nonconformist, you could have, done that for number 4, right? Would that be correct? That would be correct, right? Or any other letter you want to put in there, you want to write it that way. Any of those answers would have been okay, right? The point being, it doesn't really matter what goes in the integral of the function, what letter you use, okay? Any of these would be okay for number 4, okay? I don't know why you'd want to do that, like I said, just to be different or just to say, yeah, that is the same, and it is. I do want to comment, I told you to skip 6 and 7, because we haven't really seen this much, but what this is, if y is the same as f of x, that means you put in an x, you get out f of x, which is the y, then what would be another name for f of y? That would be x. So this is like having the equation x equals y minus 2 squared. So what this is a sideways parabola shifted to, not to the right, but since we're doing the up-down stuff, it's actually shifted up 2. So you notice it's the right half of a sideways parabola shifted up 2. Okay? Well, this would be the integral of y minus 2 squared. So you didn't have to do this, but we will be getting into this later. It would be dy, and it would go from what to what? 0 to 2. That's right, because it would be on the y-axis. We're doing area on the y-axis. Now, you didn't have to do those, but just for future reference, that is what that area would be. Okay? Now, we could actually solve this for y. We could square root both sides. Since it's only the right half of that, that would be the negative of that. So if we square root the x, it would actually be the negative square root would equal y minus 2, and then we could add 2 to that, so that'd be negative root x plus 2. So actually that is another name for that graph, and then that would be the integral of that, and then that would be dx, and then that would be from 0 to 4, because now we're talking about the x. And this integral is the same as that integral. Now, what's interesting about that is, to prove it, we could type that into our calculator right here real quick. I could just do the integral. Again, this is a little bit looking ahead, but we can go 0 to 2. What was that? It was a parenthesis. It was y minus 2. Now, you know, when I type it into the calculator, I actually don't have to use y. Just like we were just showing a minute ago, the calculator doesn't care if I put a y or a w or a t or whatever, and the calculator doesn't even need to know at this point that I'm doing that up and down version of that, right? It doesn't even know that. It would be that right there, and if I hit enter, I get 8/3. Now, what was the other one I had? I had the integral from, and it was from 0 to 4, and then it was negative square root x plus 2 dx, and I also get 8/3. It's the same piece of area, right? So we get that same thing. And then, and some of you may be curious to think, well, wait a minute, you mean I could have put that as, I could have written this one here, I could have done 0 to 2 x minus 2 quantity squared dx, and you might be thinking, wait a minute, that's a normal parabola, shifted where? To the right 2, and that would be this, and you're telling me, and then that would, right, and you're telling me that, and then the area from 0 to 2, you're telling me that would be that area? Oh, does that look like the same piece of area? It looks like it's a different graph, but it's the same piece of area. Remember, a definite integral is just a number. Just a number. For us right now, it's a piece of area. We're thinking about a piece of area, but it actually can be thought of as several different areas, possibly. Because guess what? That area is also 8/3. Different picture than the one in number 6, but it's also 8/3. So anyway, that's we'll get into that more later on, but just something to kind of be thinking of. A little bit there. All right, where's my book? Okay, so back to this. So the ones I really cared about were more in here. Any of these that you had questions about? You want to take a quick look at? Number 20. Was 19 okay? It is exactly the same. This is a half of a circle, radius 3. So that means I would go from -3 to 3. So the only difference is this one would go from -r to r. So this is also a half a circle of radius r. Okay? And so therefore, what is the area of a circle radius r? It's pi r squared, but then it's half of that, right? And then that would be it. That would be your answer. Okay? Same thing with this one. Now, let's talk to me about 17 and 18. Did anybody take this one and split it apart? Or did you just graph that? How many people just graphed 1 minus absolute value of x? How many people split it? Anybody? No? Okay, good. That's fine. I don't think there's a reason to split it. I agree. So what is that? That's a V graph upside down, shifted up 1. So it would simply be this. And right there is -1, and right there is 1. So isn't it just that triangle? Which is a 1/2, base is 2, height is 1. So that's just 1, right? Well, what would change if you went -a to a? This would be -a to a, and that would be shifted up a. So it would be 1/2. The base would be 2a times the height a. So it would be 1/2 times, it'd just be a squared, right? So that's all that would be, okay? All right. So, drawing pictures, good. What shape did 15 make? Trapezoid, right? Trapezoid. Just draw a line. Then when you do your area from 0 to 2, it makes a trapezoid. Okay, so good enough. Now, let's go into the book ones. I had, so I know we probably should talk about, what was this one, 62? And was this 66 with average value and 71? For sure I want to go through those three. Are there any before that? And that's fine. We got some time here. We should do that if there are caps. What was 57? X plus cosine x? Is that the one 0 to pi halves? X plus cosine x, 0 to pi halves. We don't know how to handle that cosine, right? And this would be, I would say this needs to be a no calculator. But this is, isn't this the one they did tell us from 0 to pi of sine is 2? They told us that. Which means if I take the sine graph and go from 0 to pi, that area right there is 2. So what that means is every hump on the sine graph is area 2. Which also means on the cosine graph the humps are 2, because sine and cosine are the same graph. They have all the same values, right? They're just shifted differently. Okay, so that's important information. So now, what I would do is split this apart. Agree? I think that's the only option you have, quite honestly. So I think we need to split this into 2, and then do each of those separately. So this one we would draw a picture. The graph is y equals x. Oh, that's off. Supposed to be a straight line. And wouldn't that make a triangle? So it would be 1/2. What's the base of that triangle? Pi halves. And the height of that triangle? Pi halves. Isn't that also pi halves? You plug it into the equation. The equation is y equals x. So you plug a pi halves into the equation. Your y is pi halves also. So it's 1/2 base times height. So that would be pi squared over 8. Would that be right? And then what about cosine from 0 to pi halves? Well, let's do a picture of that. So cosine looks like this. 0 to pi halves would be this piece right here. What do you suppose that area is? Doesn't that have to be 1? I mean, we have nice symmetry on sine and cosine, right? That's got to be half of this hump, right? So it's got to be 1. So that area's got to be 1. So pi squared over 8 plus 1. I'm curious. Even though I keep telling you this should be no calculator, but I don't see any harm in doing this to just check out things that you're wondering about or answers you have. And what was it? X plus cosine of x dx. So, if we get a picture that's geometric in shape, we can find that area. If it's not geometric in shape, right now we need some help. Right? We need some help. We need to be told something. Right? And in this case, we were told this little bit of information about sine. And that helped us. Okay? All right, good one. What else? Anything else? Or those last three? All right. So this one was tricky. This one was but essentially when you read this one, here's what would have been good to have as a thought process. Would have been, okay, they're trying to get me to show that the area is between these two amounts. Well, where in the world could those two amounts come from? What in the world would tell me that I know the area is more than that number and it's got to be less than that number? Well, here's the sine graph. Here's pi. Let's see. If I make this, I should have went over 3, not 4. So this is 3 pi 6, right? So this would be 1 pi 6, 2 pi 6, and then 3 pi 6. So here would be pi 6 right here. So we're talking about this area right here. Well, wouldn't it be true? And why? Now here's what you wouldn't have necessarily known, but what to do. But what would be an area? The only areas we know how to do right now are rectangles, triangles, stuff like that, right? What would be an area I know has to be littler than that blue area? Well, wouldn't this rectangle right here be littler than the blue area? And isn't that a rectangle I could find? Couldn't I find the height of that and the width of that? What's this height right here? How would you find that height? That's a sine curve. The sine of pi 6, right? Plug a pi 6 into the sine curve. What's the sine of pi 6? One half. Sine of pi 6, 1/2, right? 1/2. So this red rectangle has a height of 1/2 and a base of, no, it would be pi halves minus pi 6, right? Yes, it would be pi thirds. That would be 3 pi 6 minus 1 pi 6, which would be 2 pi 6, which is pi thirds. So this width here is pi thirds. So, right? So that's pi 6, 1/2 times pi thirds. So that red area is pi 6. We know the blue area has to be more than that. Right? Now, again, how would you know to draw that rectangle? Well, if you read back at one of the examples in the book, it talked about minimum and maximum. It talked about how you can trap an area if you don't know an area, which we don't know a lot of areas right now. If they're not geometric, which this one isn't, how could we trap it? Well, let's find some geometric areas. Let's find a geometric area below that and above that, and we can at least know a range of where it is. That's the idea. Not going to be necessarily a major thing you're going to have to do. Okay, but just understand that it kind of makes sense. And then what could we do for above? We could do the opposite, right? We could do this black area. Doesn't this black area have to be more than the blue area? Okay, well, what's that black area? Well, it's a height of, what's that y value? The peak of the sine grass at 1. So 1 times the width. What did we say that was? Pi thirds. 1 times pi thirds is pi thirds. So the black area is pi thirds. So there we did. We just showed. We just showed with our picture and our work that that black area, the blue area, is between those two areas, the red and the black, and those are pi 6 and pi thirds. Okay, that's what 62 is. Okay? All right. Go on to this one. 66 said the average value. So what we had to do is use that average value formula. Remember we said the average value of a function from a to b is the integral divided by b minus a. That's the average value of a function. So when they told me the average value of the function from 0 to 1 was 2, I wrote this down. And they told me the average value of the function from 1 to 3 was 4. So I wrote this down. Now what could I do with this? Well, 1, that doesn't matter, right? I mean, so 0, so the area, so the integral from 0 to 1 I now know is 2, right? And what can I do with this? 3 minus 1 is the same as 2, right? So what can I do with that? What does this tell me? Think about what I just did here. Cameron? Did you and I talk about this one? We didn't talk about it. Who did I talk about this one? Logan.
Yep.
What's that tell me? What's this tell me right here?
That is the average value.
Right, the average value is 4, but then what did we do from that? What you and I talked about this. You had already done it, as a matter of fact.
Yeah, so you want to do the integral of the 0 to 3.
Yeah, that's what I'm looking for. I'm looking for the integral from no, actually I'm looking for the average value from 0 to 3, right? Which would be this. This is what I'm looking for in my find, right?
Yeah.
Okay.
You multiply the 2 over the
Thank you, right? Multiply the 2 over here, and so now I know that the integral from 1 to 3 is 8. So now look what I got. I got the integral from 0 to 1 is 2, and I got the integral from 1 to 3 is 8. Well, what do those two pieces of information tell me? That tells me that the area from 0 to 3 is 10, right? Because of that other formula we learned yesterday. The integral from 0 to 1 plus the integral from 1 to 3 gives you the total integral from 0 to 3. Now, again, how would you know this? Well, start writing stuff down. I mean, that's the biggest thing. When people come in and ask about this, why Logan did such a good job for me. He came in and asked me about this one, but he had a lot of this already written down, right? I mean, start writing stuff down, and then you can see stuff, right? I've said this before. When you don't know what to do something, right? It may trigger the next thought. When it said the average value from 0 to 1 is 2, you should have written this down, the average value formula. When it said the integral from 1 to 3 was 4, you should have written this down, and maybe it would have come to you, oh, if I multiply the 2 over, I got that, whatever. Now, I'm not quite there yet, because they didn't want the integral from 0 to 3. They wanted the average value from 0 to 3, right? Well, the average value is this formula. Well, what's the top? What's the integral from 0 to 3? 10 divided by 3. So 10 thirds. So the final answer is 10 thirds. Okay? So that was the sequence. But how did I know to do that? Well, when they said find the average, maybe the first thing I should have written down was this right here, right? They said find the average value from 0 to 3. I should have said, oh, the formula is right there. So the average value from 0 to 3 is this. So this is what I'm looking for. Oh, so what do I need? I need to know the integral from 0 to 3. Huh. But what else did they tell me? Oh, they told me something about 0 to 1, and they told me something about 1 to 3. Oh, okay, we have a formula about that. If I can know from 0 to 1, and plus 1 to 3, right? And that would have been the thought process. Okay? All right, last point. So this is some foreshadowing of something we will be doing in Chapter 7. This is something we'll be doing a lot more of, finding areas. This is called finding the area of the region between curves. Right now we're finding just the area under a curve, or the area between a curve and the x-axis. But what we're going to go on to then is finding areas between various curves, any kind of area. So here they said, what did they say, sketch it or something? Sketch the region bounded by, and we're not going to get into this, a lot of this till later, but sketch the region bounded by the line y equals x plus 6, the line y equals x cubed, or the curve y equals x cubed, and x equals 0. What's x equals 0? The y-axis. So isn't it this region right here? Isn't that the region bounded by those? So that obviously has an area, a distinct area that we want to find. Okay, and what is this intersection point here? Does that make sense? Plug into 2, you get 8. Plug into 2, 2 cubed is 8. Yeah. So it intersects at 2, 8, right there. Okay? Now, they said sketch that region. So we just did it. Part B says express that region using integrals. Huh. Well, let's take it one curve at a time. So let's just do the y equals x plus 6. Let's call that the red curve here. All right? And if I did the integral from 0 to 2 of x plus 6 dx, what area would that be? What shape would that make? Wouldn't that be this trapezoid right here? Right? Would that give me the black area? No, it's too much. So I need to subtract off a piece of area. What area do I need to subtract off? Don't I need to subtract off this area? Wouldn't that give me the black area? Wouldn't the red area minus the blue area give me the black area? Now what's the blue area? Isn't that the integral of x cubed dx? That's the area between the x cubed graph and the x-axis, right? And so what do I need to do? I need to subtract those. So my answer then is the integral from 0 to 2 of x plus 6 dx minus the integral from 0 to 2 of x cubed dx. But wait a minute, that's two integrals. They said express the area of the region in part A. Oh, they said using integrals. So I guess that would be okay. We could stop them. But would it be okay, since we've talked about splitting apart integrals, does it make sense to be okay to put integrals back together? If you've got integrals that are split apart, could you put them together as one? And we could. So we actually could write this as the integral of x plus 6 minus x cubed dx, we could actually write that as one integral. And of course, what we're going to learn in chapter 7, which is going to take me about 10 seconds to teach it to you right now, is that when you want to do the area between two curves, you just take the area of the top curve, you just do the top curve minus the bottom curve, and that's the area between the two curves. But we got to wait for that, so, because we can't, that's too much. It's really easy concept, right? So in chapter 7, we'll do that, but we're not going to get into much of that right now. But there, I like doing this now. Again, my book kind of does this. I like to look ahead, but you can see how it comes from why we would do top minus bottom. Because basically what we're doing is we're taking that big red area, subtracting out the blue area, and that leaves us the area. Okay, it's kind of like doing the area of a ring, right? Take the outer circle minus the inner circle, that leaves you the area of the ring around that. Okay? All right, so anyway, that was number 71. Okay. So let's move on. Probably get your notes out here. Let me see what I want to do next, because this is so exciting. I don't want to screw this up. All right. So now, this part you don't have to write down here just right now yet. But get your notes ready to go here, because we will be doing a little bit of writing. And so, oh, I skipped one there. All right. You might remember earlier in the year where when we did this right here, we took the sine curve and we calculated some slopes. Remember this? We took the sine curve and we calculated some slopes. So what we did is we got on our calculators and we started here at 0, and we said, what is that slope right there? And so we picked two really close points, and we plugged them into the sine graph, and we did our slope calculation, and it came out to be 1. Let me put that in. The slope right there came out to be 1. Okay? And then we moved up here to, I left off pi 6, but that's okay. So we moved up here to pi 4s. Okay? And we said, what's that slope? And it came out to be 0.707. Okay, does that make sense? It'd be a little less. All right? And then we moved on to pi thirds, and we said, what's that slope? And it came out to be 0.8, no wait, I'm going the wrong way. Let's see, sine, it was it's 0.5, as a matter of fact. 0.5, okay? And then we went to pi halves, and of course that's an easy one. What's the slope right there? 0. And so then what we did is we said, well, let's graph those. Let's treat this as a function. Let's calculate the slopes of the sine graph. Let's treat it as a function. X is the input, Y is the slope. And we said, let's plot those. And so we plotted 0, 1, and then we went over here, pi fourths was 0.707, and pi thirds was 0.5, and pi halves was 0. And we plotted some more, and it kind of came down, it did this, and what did we say? What did we figure out? It was a cosine. Remember that? I remember you guys clapped. Some of you stood up even. I remember that. It was like yelling and screaming going on. Remember that? Yeah, it was really cool. And maybe I thought of it. Maybe I was dreaming. Maybe that's kind of dream. I remember I did that great lesson. They all stood up and cheered. Yeah, I remember that. Yeah, that's what it was. All right. So anyway, and so thus was born the idea of the derivative function, f prime, right? F prime. What f prime is a plotting of the slopes of the f function, right? And it was its own derivative. And f double prime was a plotting of the slopes of the f prime, right? Right? We know that. I mean, that's what f prime is, the slopes. But it's its own function. It's called the derivative function, and it is a plotting of the slopes of the original function, or the f function. Okay. So what we want to do is that very same thing today with area. We want to, instead of finding just a single piece of area, we want to talk about finding a variety of areas. So what we're going to do, and now it's a little more complicated because with derivative, it was easy to create a function because x was the point where we did the slope. Do we do area at a point? Where do we do area? Between a left endpoint and a right endpoint, correct? So here's what we're going to do. We're going to fix our left endpoint. Now, I'll just pick 0 to start with, but it could be anywhere. It could be at 1 or 2 or whatever, 3, okay? So we're going to fix our left endpoint and not change it, but our right endpoint is going to change. So our x is, this you could write down. This you could write down. And you could title it, this is the concept of an area function. Just like we had a slope function. Now that was called f prime. The slope function was called f prime. We don't really have a name for the area function right now. We'll just call it big A of x for right now. A for area. Big A of x. But our input into that function is the right edge of our area. So it's kind of unusual. But it kind of makes sense that it would be a function, because remember, a function means for any one input, you only have one output, right? So if we move to a new right edge, we get a new area. How many areas do you get for every right endpoint? 1. You move your right edge, your left edge stays at 0. You move your right edge, you get an area. Only one area. You move it again, you get another area. You move it again, you get another area. Right? All right. So it does make a function. Now in here, we just have some little f function. Now here's where we have a little bit of a dilemma. What letter do I put here? Can I put x here? I cannot put x here because I'm already using x for something else. I'm using x to be the right edge. And let's draw a picture of this here. I've got my little f function here. Okay? But I can't, and I'm using 0 is my left edge, and over here I'm using x as my right edge of that area. So I cannot use x as my variable for my function. So I got to use something else. Usually we use t. Okay? Now that will cause some confusion for people, okay, as we go along. And we just got to remember that it doesn't matter what's in here when we've got an x or whatever we have up here. Whatever we have up here, I could put a t up here or a z or something else, right? But we usually use x. But whatever letter's up here, I cannot have that same letter here because they're two different things. Okay? So we usually have x up here, and then whatever's here just has to be something other than x. And it doesn't matter. It could be w or u or t. It's usually t. But it could be something else. Like, remember I said something about like a dummy variable the other day, just kind of thing. Okay? All right. So this column's going to be my area then, right? This column's going to be my area. So this is an area function. This is a function, right? Remember, to be a function, all you need is input and output. And for every one input, you can only have one output. Okay? All right. So it kind of makes sense that when x is here, we'd have an area. If I move x over here, so you got to kind of think of the x as being able to slide back and forth. Right? Being able to slide back and forth. Matter of fact, I've got kind of a picture here. Think of it this way. Right? This area is changing. Notice I wrote this f of t is 3t plus 2. The area from a to x, a could change. I could move my left endpoint here. Right? But once we fix our left endpoint, say there, now, okay, I got an area here, got another area, got another area, got another area, another area, and I could make a whole table about it. And then I could graph those, which we're going to do here in a little bit, and kind of see what that looks like. Just like we did back here when we did slopes. We went to this point, found the slope. 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 Then we plotted those points, and it was like, voila, there's our derivative function. Okay? So we're doing the same thing here with area. New right endpoint, got an area. New right endpoint, another area. Another right endpoint, another area. Okay? All right, so I think at this point, it might not be a bad idea to just pass this out. I think what we're going to do here, just for the sake of time, is just kind of go through this together. So we're gonna try this with just a couple of different functions here. Where am I? Okay. So this is the document. I'm going to send it to you. We'll just go through this worksheet together here. So we're going to fill in that little table here. So notice what you have here. We've got the function right here. Now in your paper, in your little table there, you've got the x column, and then you've got the integral from 0 to x of 1.5 dt. So that means our equation here is y equals 1.5. So here it is right here. Right? This is the equation y equals 1.5. So I went ahead and drawn it. If you want to draw it off to the side, you can, so it makes sense to you, you know, where you have that little space out to the right. If you want to draw a little picture of just y equals 1.5, because that's what our integral is here. Okay? So we'll start with a very simple function, just a horizontal line. Okay? So, the first entry in the table is we want to have an x of 1. That means, now again, understand, everybody look up here. Having an x of 1 means putting a 1 right there, right? When we talk about an x, we talk about plugging it in for the x. Well, that's what we're doing. That's why we can't have an x inside here, right? We don't want to plug this 1 inside here. It goes in for that x right there. So when we do 1, we're doing the area from 0 to 1. When we plug in a 2, we're doing the area from 0 to 2. When we plug a 3 in for x, we're doing the area from 0 to 3. And then the area from 0 to 4, and then the area from 0 to 5. Does that make sense? Every time our input to our area function is the right edge. Because remember, see, with slope function, our input was where we wanted to do the slope. It's the x value we were doing the slope. But you can't do area at a point, between 2 points. So we have to fix the left edge, and then our right edge is our variable. Okay? Our right edge is what's changing. Okay, so plug in a 1, it's the area from 0 to 1. Plug in a 2, area from 0 to 2. Plug in a 3, it's the area from 0 to 3. So, back here, then on this, we've got them calculated. Well, this is easy. It's 1 wide and 1.5 tall. That's an area of 1.5. So fill in the table, right? So when x is 1, y is going to be, our area is going to be 1.5, right? What's the next one going to be? It can be 2 wide and 1.5 tall. That's going to be 3. And then let's slide it over again. 4.5, right? You probably got it all filled in. Then 6, then 7.5. Right? Now, what do we want to do next with this? Well, let's answer the question. So for every 1 unit that x changes, how much does the area change? 1.5, right? Good. Fill that in. For every one, oh wait, right here. If x equals 0, what is the area? That'd be the area from 0 to 0. That would be 0, right? Okay? Number 4, if you were to graph the ordered pairs, what would the graph look like? What do you think? Caleb? Wouldn't it be a line? Go over 1, up 1.5. Go over 1, up 1.5. Go over 1, up 1.5. Now I'm going to do it here on the screen here. So you guys tell me. So what do I plug in right there? I plug in a 1.5, and then a 3, and then a 4.5, and then a 6, and then a 7.5. That would be the area function. So let me write that down here. So what we're saying, if I'm hearing you correctly, I think what you're telling me is we had little f function was 1.5, and what was the area function? What is that? What's the equation of that line? Okay. All right. Now let's change to this problem. 1/2 t. They write it t over 2. Let's write it 1/2 t. 1/2 t. Oops. Okay, so let's go on your paper here. Okay, moving on. Let's skip that other stuff. Okay, now we're going to change this to 1/2 t. All right, well, what's the graph of 1/2 t look like? Y equals 1/2 t, and we could call it y equals 1/2 x. Over here, listen, over here it's okay to use x. If I'm out over here and just writing down and thinking about this function in here, I can call it 1/2 x. I just can't put an x in there when I put it inside the integral, right? When I've got this x up here, I can't have an x in there. But that's 1/2 t. Yeah, that's just like we've been saying, u squared, w squared, t squared, x squared, those are all parabolas, right? So I can think of this as the line y equals 1/2 x. But when I put it inside the integral, I got to put 1/2 t. Okay? All right. So now, so you put a 1 in there, that's going to be the area from 0 to 1. So this is going to be the area from 0 to 1. This is going to be the area from 0 to 2. This is going to be the area from 0 to 3. This is going to be the area from 0 to 4. This is going to be the area from 0 to 5, right? Now, there's nothing magical about the 0. We've just chosen 0 to be our left endpoint. It could have been 1, could have been 2, whatever, but it stays fixed throughout the problem. If you change the left endpoint, aren't you going to have different areas? It's going to be a different function, isn't it? Because the areas are going to be different, right? Because if that was a 1, then if the left endpoint was 1, then this would be the integral from 1 to 1, and 1 to 2, and 1 to 3. And those would be different areas, okay? And we'll get into that later. We don't worry about it right now. Okay, first of all, question 8, if x is 0, what's your area? Again, it'd be the area from 0 to 0, so that's just 0. Okay, let's fill in the table. Now, this one's going to be a little harder, okay? Not harder, but now we got a triangle. Now we got triangles, don't we? So what's this area? Well, we'll just copy it down. It's 0.25. Because it'd be 1, and it would go up a half. So if you plug in a 1, you get a half. So it'd be 1 times a half, because it's half base times height. So it's 1/4. Okay, but now, look what happens now when we go over to 2. Now the area is 1, so fill that in. Right? So how much area did we gain then? 0.75, didn't we? Okay, now let's go up, let's slide over another one. Now the area from 0 to 3, we got 2.25. How much do we gain there? Okay, and then go over another one. Now the area is 4, right? And then go over another one. Right? And we got that. So I think I wanted to ask a question, but I think they asked it here. Explain why when x increases by 1, the value does not increase by the same amount. Like the last problem, right? It kept going up 1.5 every time. Why isn't it going up by the same amount? It's easy. So since it's diagonal, yeah. So every time you go over 1, you're gaining a bigger chunk of area? Does that make sense? I mean, right? I mean, look at the picture, right? So every time I go over 1, every time I make my right endpoint 1 bigger, I'm gaining a bigger and bigger chunk of area. Every time I go over 1, I'm gaining a 1 wide chunk of area, but it's a lot taller each time, right? So I'm gaining bigger and bigger chunks of area. So if I plot this, what should happen? What did we have? 0.25? What was the next one? 1, 2.25. What was next? 4, 6.25. Okay? Looks like that. Is this graph linear? This graph I was just graphing those points. What do you think it is? It's a parabola. Turns out it's a parabola. Okay? Now, we don't know exactly what the equation is, but it is a parabola. So we started with, so what you're telling me is we started with little f was 1/2 x, and we ended up, and our area function, big A, was some sort of parabola. Right? I don't think it's just x squared, but it's some sort of parabola. Okay? So you're probably already seeing what's going on here, right? What are you noticing with your area function? first one we did was this. Little f was 1.5, and big A, the area function, was 1.5x. Antiderivative. Doesn't it seem to be happening? It seems to be an antiderivative. Now, that probably doesn't come as any kind of surprise at all, because when we started this, we were doing position velocity stuff, right? Remember that? And remember when we did a velocity graph and we did the area under it? What did it give us? Position, miles, didn't it? It gave us miles. Well, what happens when you go that direction in that list? Isn't that antiderivative, right? When you go from miles per hour to miles. So it's not a big surprise, right? Not a big surprise. It's antiderivative, but still pretty cool. I mean, the fact that slope and area, which seem to have nothing in common, right, are kind of these opposite or reverse processes. Now, from the standpoint of how you go about it, if you just think about miles and miles per hour, position velocity, that's a division. That's your y's divided by your x's, which of course is what slope is, rise over run, right? And what antiderivative seems to be is when we did this the other day, we took miles per hour times hours. That's how come we got miles, right? We took miles per hour times hours. So it seems like when we do an area, we're multiplying. Yeah, well, that's true, because length times width, right? We're multiplying. So slope is dividing, area is multiplying. Well, those are kind of reverse processes, aren't they? Multiplying and dividing. So in a sense, it makes sense that area and slope are like reverse processes. Okay? So if the dividing in slope is called derivative, then going the other way, antiderivative, so it does all kind of fit together. Okay? So how is that all going to play about? Well, if the antiderivative, that's what it is. So they give me one last thing to look at here. If that's really what's going on here, here's another function right here. Okay? And here's this area. Okay? Now, watch this number right here, the area, and tell me what's happening with that as I drag this along. Okay? So I start here with no area. And as I drag this, what happens to that number? It's increasing. So what you're telling me is that area is increasing right through here until right here. Now what happens to that number? Why is the area decreasing right now? Because I'm picking up negative area, right? And I'm going to keep picking up negative area until right there, right? So the area is going to keep decreasing till here, and then what happens to that area? Starts increasing because I'm picking up positive area. So it seems to me that the area function here, if I compare it to little f, the area function started out increasing right through here, while little f was positive. And then the area function started decreasing right through here, while little f was, okay? Well, doesn't it make sense if the chart stuff would still be good, right? Because it's the antiderivative. So if this is little f, the antiderivative is big A. We could call our area function just big F, right? That's kind of cool. So that graph right there, little f, this graph called little f, if we think of that as our derivative graph, all the stuff we thought about as slope, all the stuff in the chart was slope, right? When we thought about this in the chart before, we said the slope's positive, the graph goes up. Oh yeah, it does. And slope's negative, graph goes down. Yeah, we know that all the way from Algebra 1. But the same thing's true when we think about it in terms of area. The area under F, now again, whenever we talk about increasing, decreasing, we're always talking about as we go from left to right. So as I go from left to right, as I come in here from left to right, I'm picking up positive areas, so my area is increasing. And then I start picking up negative areas, so my area is decreasing, 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 right? Same sort of thing. So I'm describing that original function, that area function. Let's look at another version of that right here, okay? This dot right here is the area being plotted, okay? So let's come back here. Oh, whoops. Okay, so right here I have zero area, right? And as I slide to the right, I'm picking up what? positive area, right? And look at that area graph. And I'm picking up bigger and bigger chunks, right? So what do you suppose, is that dot going up in a line? It's curving, isn't it? It's curving. It's going to keep going up and up and up. Now let me slide way over here. Now here's where we got to start thinking about the left endpoint. Notice my integral is from a to x. From a to x. So what does that make this area here? Positive. Now I think everybody's with me pretty well. So what the heck? Now that I got everybody figured it out, we always want to throw something new to confusion, right? Okay. Yeah, that's the way it goes. But okay. But we'll have, just like we did when we originally did the chart, we'll have days of working this out to put it all together, right? So this is positive area, right? You with me? Because we're going from A to X. We're going back. And this is negative area. Okay. So this X is still my right endpoint, right? It's still the input of my area function. It's still this guy up here. Okay? It's just back. All right. So as I go this way, from left to right, what's happening to my area? Why is it decreasing? Think of the orange as my area. Aren't I losing area? And what did we say this area was? Positive. So if you lose positive area, remember we used to talk about getting negative and more negative or less negative? Remember that? That's kind of the same thing here. I'm losing positive area. The orange, I'm losing it, but it's positive, so therefore my area is coming down. I have more positive than negative, so my total area is positive right now, right? But what happens when I get right to there? What's my area? 0, because the positive's canceling out the negative, right? But I'm still losing area, right? I'm still losing positive area. So my area dot is still going down. Losing area, losing area, losing area, losing area. Okay, now, overall, though, my area is negative, isn't it? Because I got more negative than I got positive. That's why the dot's down here. Keep going. I'm losing area, losing area, losing area. Oh, what happens right here? I quit losing positive area, and now I'm losing negative area. What happens if you lose negative area? You're actually gaining area. It's not going to be positive. No, look at the area. It's still down here below, right? I still have negative area, right? But right now, the orange is, I'm getting less orange, but the orange, remember, is negative. So I'm losing negative area. So that means my area is going back up. It's negative and getting less negative, right? So what did I have right there? Is that a local min? Oh, look at the little F graphs going from negative to more chart stuff, right? More chart stuff. Okay? Losing negative, losing negative, losing negative until right there my area is 0. Now I'm going the right direction. Now A to X is going the correct way, right? I'm not backwards anymore. So what's the area I'm picking up now? Positive. Like so. Okay. Now, let's graph that. So is it surprising that's a parabola? You have a line for little f. We said it's antiderivative, so the area is going to be that, right? So the area should be a parabola. It's antiderivative. And sure enough, we just saw, it seems to make sense that that's what's happening. Losing positive, the area is going down, 0 area there, okay? Minimum there, because I've lost all my positive area. Now I'm losing some negative area, so it's climbing back up. Now I get back to 0 area, and now I'm going to gain positive area for the rest of the time. Now, if I change that left endpoint, well, aren't I going to get different areas at all those places? But the little f's not going to change. Will it shift? You're talking about the parabola. Will it just shift the parabola? Because what if I change that left endpoint from 0 to 1? What will be the difference in all those areas when I move x now? It'll just be that piece of area from 0 to 1 will be the difference in all those points. So they'll all be different by 1 value. Watch this. You're exactly right. When I shift the left endpoint, it just makes that graph. So let's move it to there. So all the same things apply. This is still positive area. This is still negative area. I'm still losing this negative area through here. My 0 is now over here where it was here before, right? My minimum still happens there. The blue graph never changed. So doesn't the minimum still always have to happen there? Oh, wait a minute. You mean when I go from an F to a big F graph, the only difference is the... Didn't we say that? Remember in chapter 1 when I gave you an F prime graph and told you to graph the F graph? Wasn't that doing an antiderivative? And we didn't know where to start, remember? Because what? Because there's some shift. When you actually do the antiderivative, if you actually want to do the antiderivative of 1.5 and you want to call that big F or big A, whatever, that's 1.5x plus... Isn't that it? Isn't that it when you do the antiderivatives of plus c? That's a shift. So that minimum stays there. So if I move that left endpoint, yeah, that minimum stays there. All this charge stuff is still there. Okay, so anyway, so I move the x, and so again, I'm losing this negative area, so it's coming back up. There's my 0 now, is there. Okay, and then gaining. All right. There's a lot of just heavy-duty concept there, not a lot of problems to solve, really. What has happened, though, is if you get a set of problems that deal with an area function, in your head you should just be thinking, okay, that's antiderivative. So think of the chart. You're going to be asked some kind of chart kind of questions. I want you to try to think of them in terms of areas now, like we did here, not in terms of slopes. Okay? But they're still chart kind of things. But in your head, I want you to be thinking about what I did here with sliding. I want you to envision this idea of sliding and where would the area be. But if you move that right endpoint, right, what would happen to this orange? Visualize that orange area kind of changing as you go. Okay? And think about, am I gaining area, losing area, that kind of stuff. So what we're going to try to do over the course of the next few days is take all those chart kind of representations we have, since we've now figured out that the area is the antiderivative. Take all those chart representations that involve the antiderivative and apply them with area. Think of them with area, not slope. Okay? That's what the homework's going to be like. Okay, let's look at what a problem would actually look like with that. Okay? And so let's do this problem right here. Okay? So you know what I mean? Because right now it's been just a lot of conceptual stuff. So the very first problem in your homework is going to look very much like this, okay? It's going to be kind of an offshoot of this, all right? So let's go ahead and do this one together. So it says, let little f be x plus 3. Now notice we use the x there, right, in there, because that's outside the interval, so that's fine. It says let a of x, our area function. Here in the beginning we'll call this a of x, later we'll call it big F, big G. Excuse me. Since we know it's antiderivative, right, it's capital F. So, hyperventilate. All right. So, big A, the area function, is the... Now, notice we're using 2 here as our left edge, right? Okay. So, 2 is our left edge to x. And notice in here that I write t in there. It's still little f, but I go ahead and write t in there. Now, what I could have written here, I could have written it, let's do that. Instead of little f of t, I could have just written what? Let's write this function in here. What would it be? T, I heard it. T plus 3, thank you. T plus 3 dt, right? Sometimes you just write it little f. Okay, sometimes you just write it little f. But we could, this is little f. Little f is x plus 3, which we can write w plus 3 or u plus 3 or t plus 3, anything we want. We just can't use x when we put it in here because we're already using x for that. So we got to use something else. Okay, so let's graph it. T plus 3. So that'd be up 3, y-intercept, up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Okay, and let's draw that thing. And this is little f now. Little f. And I think the problem says, I think the problem in your homework says, find a formula for big A. What we're trying to do, here's what the problem is. Find a formula, which means an equation, for big A of x. That's what we're trying to do. Trying to find a formula for big A. Okay? Now we already kind of know it has to do with antiderivative a little bit, right? We know it has to do with that. So let's see that it truly does. So big A, the area, is going to go from 2 to x. So let's draw it. So here's 2. Here's my left edge at 2. Now my right edge is going to be x. Now we just showed with that other thing with the orange that I could move the x on the left side and it still works. But it just makes it more complicated. So let's leave the x over here. So I'm not going to put it right at 4 or 5. I'm just going to put it in between here somewhere. Whatever. It's just that, and remember, that can slide. So imagine this is that orange area here. Right? That's that orange piece of area. And I can take that right edge and I can slide it to different places. Okay? It's a function. Different x values, different outputs, different areas. Okay. Well, what we want to do is write a formula for this area. Well, what shape is that? It's a trapezoid, so we can do it. So our area is going to be 1/2. What's this base right here? Isn't that 5? Is that going to change? No. As we slide the x around, that is not going to change. So that's going to be 5. Plus, no. What is this?
5 plus x.
No. I'm pretty sure. It's x plus 3. Now let's think about this a minute. How did you get 5 here? You plugged a 2 into this function. Right here or right here for the t, doesn't matter. 2 plus 3 is 5. Well, how are you going to get this y value? You're going to plug an x into the function. So you plug an x in for x, or for t, you get x plus 3. So this y value here is going to be x plus 3. It's going to change, right? When you slide that right edge, that y value is going to change. So it's got to have an x in it. Okay, so base 1 plus base 2, and then the height. What is this height right here?
X minus 2.
X minus 2, right? You got to subtract those. So let's put that in parentheses. X minus 2. So let's work this out with a little algebra. We got 1/2. We got what? X plus 8. We got x minus 2. So we got to FOIL that. So what will that be? That'll be x squared. 8x minus 2x, that'll be 6x. 8 minus 2 is negative 16. Correct? So that's, now let's distribute the 1/2. And that's going to be 1/2 x squared plus 3x minus 16/3. Oh, why did I say thirds? That was dumb. I don't know what I was thinking. What will it be? Minus 8. Again, lack of oxygen. I'm just barely hanging on over here. All right. So, 1/2 x squared plus 3x minus 8. Correct? Now, let's bring in this idea we just had of antiderivative. If I had asked you before this problem started to do the antiderivative of this, what would you have done? What's the antiderivative of x? You raise it up to a 2 and divide by 2. 1/2 x squared. What's the antiderivative of 3? 3x. Plus some c. Now, we're going to do that in a minute, and I'm going to show you how to find the c. Because, isn't that amazing that that came out of a trapezoid? Right? Look at it. That antiderivative came out of a trapezoid formula. It came out to be an antiderivative. That's just amazing. Now, let me do this in a different color. So what we've learned, because here's the key. The only reason we were able to do that is because it was a line, because it made a trapezoid. If I would have given you a parabola there, would we have had a geometric shape that we could have done? We would not have. So that's really cool, but it's really limited. It wouldn't work for most things. But now that we've learned it's an antiderivative, now we could have done this. We could have said, oh, okay, I know my area function is going to be the antiderivative of that. It's going to be 1/2 x squared plus 3x plus some c. Now, how in the world can we find that c? Well, to find the c, you got to know what? Think differential equation. Initial value problem. To find the unknown c, you need what? Some initial condition. Some point. On the A graph, right? Is there any area here that we know for sure? I say there is. See this little 2 down here? You know the worksheet we were just doing a minute ago? That one question they always ask you? What if x is a 2? What if x is a 2? Isn't the area 0? We know that. That's an area we know for sure. Now, since this happened to be a trapezoid, we could have found the area at anything, right? But if it wasn't a trapezoid, it was an x squared or something like that, it wasn't a geometric shape, we wouldn't know any areas. But there's always one area you know. Whenever you have an area function, there's always one free initial condition that comes with it, right? Whatever your left edge is, you know if you put that number in there, you're going to get an area of 0. So we know that a of 2 is 0. So now what can we do? We can put a 2 in for the x. So we would get 1/2 times 2 squared plus 3 times 2 plus c, and we know that's got to equal 0. So that's 4 times 1/2 is 2. 2 plus 6 is 8. 8 plus c is 0. So we know c is -8. Sure enough, we could then take that right back up there. We could put that c in there, that -8, and there is our trapezoid equation we got. There's our antiderivative. All right. So the big lesson from today is.
Could you go back?
Yep. So the big thing, the big takeaway from today is the area function is the antiderivative of what you're doing the area, the function you're doing the area. Okay? So the area function, and I'll just put an a in there, little a, call that f of t dt, is the antiderivative of little f. Okay? The area function, we call it big A generally. And in your book they do this. They go big A with a little f down here. They call it big A of x, saying meaning the area under little f. Okay? But I usually won't write that. It's big A. Okay? And they might use big F or big G on some problems. All right, so you're going to do in section 5.2, 2 through 11. Now 2 probably takes the longest of all of it. 2, and then 3 through 8 is a section. It's funny on the video, you probably see, I might have mentioned the video. Last year when I wrote down this homework, I said, okay, we're going to do 2, then we're going to do 3 through 8, then we're going to do 9, and then 10, and then 11. And finally, about 10 minutes later, whenever I couldn't figure out why everybody was laughing, I realized that was 2 through 11. But the reason is, in the homework, they're like different sections. Whatever. Anyway, so anyway, I don't want to make that mistake again. We're going to do 2 through 11. Number 2 is just like the one we just did. They give you a function, little f. I want you to draw the picture. I want you to do the geometry like I did here. And then if you want to, also do what I did in blue here with the antiderivative and show that they come out the same. Okay? And so just some practice and you trying that on your own. Then 3 through 11 or 3 through 8 are more like kind of chart kind of things. Sort of. But I want you to think of them in terms of area. like when I was sliding that thing with the orange. Okay, so I kind of want you to try to think of it those terms. All right, and again, I won't be here tomorrow. It's not a, it just doesn't work out good. Well, I mean, it's fine. I mean, you're going to hear the same thing in that video that I would be saying. But we will definitely take some time Thursday to go over and whatever issues you may have had. But make sure you watch it. I mean, you need to watch it because you'll be missing a lot. Okay, so that's all you're going to do with class time. And then take notes like you would the assignments. And then we'll get it all together on Thursday. We got a little bit new to do Thursday, and then Monday we'll just really put it all together. Probably plan on Tuesday quiz. Like Monday won't really be any new stuff. We'll just really review. Okay. All right. In case you have questions.